In this study, researchers integrate the obstacle problem formulation from ice sheet modeling with deep learning methodologies to enhance ice thickness predictions, focusing on the Greenland ice sheet. They harmonize the mathematical structure with an energy minimization framework tailored for neural network approximations, confirming the method's efficacy through 1D and 2D numerical simulations. The study utilizes the NSIDC 0092 dataset for Greenland and incorporates bedrock topography for model pre-training, registering notable advances in prediction accuracy. This research underscores the potent combination of traditional mathematical models and advanced computational techniques in delivering precise ice thickness estimations. This research paper presents a mathematical formulation of an ice sheet model, adapted from previous works, to study the ice thickness variational inequality. The model is defined on a bounded and connected open subset of the two-dimensional Euclidean space, denoted as omega, with a Lipschitz continuous boundary. The bedrock elevation is represented by the function b, while the elevation of the top surface of the ice sheet is characterized by the function h, which always maintains a value greater than or equal to b. The thickness of the ice, denoted as h, is non-negative throughout the domain omega. The relationship between h and b implies the existence of a free boundary, defined as omega plus equals h greater than b equals h greater than 0, which separates the region where the ice is present from the region where it is not. The associated free boundary is expressed as gamma f equals omega intersection partial differential omega plus. The source function a, which denotes ice accumulation, is positive within omega plus, while it is negative outside omega plus, indicating ablation. The basal sliding velocity, ub, is a vector field contingent on the lateral position, and is 0 when the ice base is in a frozen state. The horizontal ice flow velocity, u, is computed using the surface elevation h and its gradient. The viscosity of the ice is described by the Glenn power law with ice softness coefficient a, x, z, and exponent p, whose values are suggested by laboratory experiments. The ice sheet model is formulated as an obstacle problem, where the bedrock acts as the primary constraint, and the changes in ice thickness are studied as a variational inequality. This formulation is essential for understanding the dynamics of ice sheets and their response to climate change. Here is a combined summary of pages 5 and 6. The paper formulates a mathematical model for the morphology of ice sheets, incorporating the impact of gravity and iceflow velocity. The surface elevation h is governed by equation 6, which is derived from the continuity equation for incompressible flow and the correlation between the ice surface motion and the mass balance data. This equation is simplified to equation 7 when the coefficient a, x, z is assumed to be constant. To form a weak solution for problem 7 over the entire domain omega, the absence of volumetric ice flow towards omega is posited, and the volume flux q is extrapolated to be 0 outside omega plus. The variational inequality 12 is then derived by multiplying equation 5 by a smooth test function v and integrating over omega, applying Gauss's theorem, and using the conditions q equals 0 and a is less than or equal to 0 within omega. The volume flux q exhibits degenerate behavior at the free boundary, which is addressed by introducing a transformation h equals u caret p1 to p from 3. This transformation yields a transformed version of equation 7, given by equation 14, where micro x, u, and phi x, u are specifically defined functions. To simplify the nonlinear dynamics, the paper makes specific assumptions, including ub equals 0, psi x, u equals 0, and micro x, u equals micro 0. Under these assumptions, the inequality 12 simplifies to equation 15, which is a key result of the paper. This equation forms the basis for further study and applications, including the implications of the transformed equation and its potential to model real-world ice sheet morphology. Here is a combined summary of pages 7 and 8 of the research paper. The inequality holds for all v is greater than or equal to 0 defined over omega and p is greater than or equal to 2, with micro 0 equals 1 taken for simplification. The paper builds upon the seminal work by the original authors, who identified inherent n online arities that were not thoroughly explored. This research focuses on two primary n-online arities: the PLA place-type nonlinearity arising from Glen's flow law and the intricate nonlinearity in phi x u due to the bedrock gradient nabla b. The PLA place-type nonlinearity is examined for cases where p greater than 2, introducing complexities that were not addressed in the original study. The nonlinearity in phi x u is explored for scenarios where the bedrock elevation is not flat, introducing another layer of nonlinearity. The energy minimization formulation is introduced, where V is a Hilbert space such that V element of H1, omega, and U is a subspace defined by the Dirichlet boundary condition. The constraint set K is defined as the set of V element of V that satisfy V is greater than or equal to B in omega and the Dirichlet boundary condition. The variational inequality problem is equivalently posed as an energy minimization problem, where the goal is to find U element of K such that J, U, is less than or equal to J, V, for all V in K. The energy functional J is defined as J, V, equals B, V, V, A, V, where B, V, V, is a PLA place-type term. A regularization term is introduced to the energy functional, leading to the augmented energy functional L, V, equals J, V, plus alpha integral omega, B, x, V, x, 2 plus dx. Based on previous findings, the unique solution U of the regularized problem approaches the solution of the original problem as alpha grows large. This leads to the minimization problem MINV element of VL, V, with the energy functional given by L, V, equals 1, P, integral omega, nabla V psi, P dx integral omega avenue dx plus alpha integral omega, B versus 2 plus dx. In numerical computations, the continuous energy functional is approximated by its discrete counterpart, L, V, equals, omega, n airy summation I equals 1, P, parallel nabla V, xi, psi, xi, parallel P, 2 xi, V, xi, plus alpha, B, xi, V, xi, 2 plus, where xi are the discretization points. Here is the combined summary. The minimization problem is generalized to accommodate non-zero solutions on the boundary, with the modified energy functional L, V, defined as the sum of four terms: the norm of the difference between the gradient of V and psi, the integral of avenue over omega, the squared difference between B and V, and the squared difference between versus and H on the boundary partial differential omega. To approximate the solution, a fully connected feed-forward neural network F. Road right-pointing arrow RND is employed, comprising multiple layers with nonlinear activation functions to capture complex relationships. The network's weights and biases are refined iteratively using backpropagation to minimize a loss function derived from the energy minimization formulation. The composite loss function consists of three primary components: the residual loss, which measures the degree to which the current solution fails to satisfy the PDE; the obstacle loss, which penalizes the discrepancy between the network's output and the obstacle function B; and the boundary condition loss, which ensures the solution adheres to known values on the boundary. The total loss function L, theta, is a weighted combination of these losses, with coefficients alpha and beta balancing the importance of PDE satisfaction, constraint satisfaction, and boundary condition satisfaction. The optimal values of alpha and beta are attained through iterative trial and error to ensure a balanced representation of all problem constraints. The training process employs a batch approach, where data subsets iteratively refine the network parameters. This approach enables the neural network to capture intricate nonlinear relationships and approximate the solution efficiently. The efficacy of this method is showcased in subsequent sections, highlighting the neural network's practical applications and versatility in solving complex PDE problems. The authors outline a sequence of numerical experiments to test the deep learning approach for solving partial differential equations with obstacle constraints. The method of manufactured solutions is employed, which involves creating an exact solution for an augmented form of the PDE, allowing for a comprehensive assessment of the numerical method. The approach is first applied to a simpler PDE with an obstacle constraint in 1D and 2D domains, followed by a more complex PDE with the constraint. The solution approximator adopts an architecture comprising a minimum of 5 hidden layers, each with 128 neurons, utilizing the squared rectified linear unit and layer normalization techniques. The optimization phase employs the atom variant of stochastic gradient descent with a learning rate schedule determined through trial and error. The primary objective is the minimization of the associated loss function, implemented and trained using the PyTorch library. The authors acknowledge that variations on this network and training structure could be investigated, but the focus is on feasibility rather than refinement. The 1D example with p equals 2 is considered, using an obstacle function characterized by a piecewise definition. The exact solution is also piecewise defined, and a visualization is provided in Figure 2, comparing the 1D solution, obstacle function, and exact solution. The deep learning approach is validated through the method of manufactured solutions, providing a ground truth for rigorous comparison. The authors aim to assess the robustness and accuracy of this approach, which is essential for solving complex PDEs with obstacle constraints. The experiments are designed to demonstrate the feasibility of the approach, with refinement left for future study. The results of these experiments will provide insight into the performance of the deep learning method in solving PDEs with obstacle constraints, paving the way for its application to more complex problems, such as finding the elevation profile of ice above the bedrock of Greenland. The research paper discusses the training of a solution approximator for a specific problem. The approach involves modifications tailored to the problem specifics. The neural network undergoes training over 2,000 iterations with fixed regularization parameters. The performance is assessed on a mesh grid with a fine resolution of 10-3. The numerical solution is presented in Figure 2, juxtaposed against the obstacle function and the exact solution. The training dynamics are charted in Figure 3, showing the evolution of various loss metrics. Notably, the proposed technique converges within 500 iterations, highlighting its robustness and efficacy. The paper also quantifies the difference between the exact and approximated solutions using the L1 norm, providing insight into the loss versus iterations. The paper presents a novel approach to solving partial differential equations, PDEs, using neural networks. It leverages the power of deep learning to approximate complex mathematical models, providing insights into the convergence behavior and accuracy of the neural network's predictions. The results demonstrate that this approach learns a neural network approximator that accurately learns to solve the PDE subject to the given constraints. In the analysis, the authors examine the accuracy of this approach as a function of the number of sampled points at which the PDE loss is computed. This analysis provides insights into how the sampling granularity can influence the accuracy of the derived solution. The sample points are systematically chosen from a uniform grid, ensuring consistent and unbiased assessment. Figure 5 portrays the relationship between sample size and the resultant relative error. The plot highlights the reduction in relative error as sample count augments. A linear regression on the log transformed data points results in a slope of approximately 0.83, indicating that the actual slope from the data lies between the theoretical slopes of 1 and 1/2. Therefore, the error reduction behavior in the analysis is intermediate between these two theoretical expectations. The analysis illustrates the reduction in relative error as the computational grid is refined. Common computational PDE approaches, finite difference, finite element, etc., produce errors that scale as 1n, while Monte Carlo approaches commonly lead to errors that scale as 1 sqrt n. To visualize the scaling relationship between error and number of points, n, Figure 5 is plotted on log-log axis and a regression line is fit to the error magnitude to compute the scaling slope. Results indicate that errors decay faster than 1 sqrt n, but more slowly than 1 n for the range used. In the analysis presented, the impact of sampling and the influence of varying regularization parameters and loss weighting parameters on relative error were comprehensively explored. This understanding is crucial for ensuring the model captures underlying patterns effectively without overfitting or underfitting. Table 1 illustrates the relative errors for different values of the regularization parameter, highlighting the need for a proper balance between the loss components. The study then shifted focus to the 2D problem with p is greater than or equal to 2, using uniformly sampled collocation points and a circularly symmetric obstacle function. An exact solution within the domain was constructed, showcasing the neural network's approximation capabilities. Figure 6 presents the obstacle function, exact solution, and the neural network's approximation for p equals 3. The training process efficiency was illustrated through losses on a logarithmic scale against the number of iterations, and the L1 norm of the difference between the approximated and true solutions as a function of training iteration was also shown. This comprehensive analysis and presentation of results demonstrate the significance of the study in understanding the dynamics of model training and its impact on solution accuracy. The research paper presents a comprehensive analysis of the evolution of different losses during training and the convergence behavior of a neural network in solving an obstacle problem. Figure 7 illustrates the evolution of various losses over the number of iterations, including the total loss, loss 1, loss 2, and loss 3. These losses are influenced by coefficients and equations, providing insights into the neural network's performance and prediction accuracy. In Figure 8, the L1 error for p equals 3 between the approximated solution u** operator and the exact solution u is shown. This plot highlights the neural network's convergence behavior and prediction accuracy for this parameter setting. For the case p equals 4, the paper presents results using the same methodologies. Visual representations of the obstacle function, exact solution, and the neural network's approximation for p equals 4 are presented in Figure 9. This figure includes the obstacle function plot, exact solution plot, and approximated solution plot, showcasing the neural network's performance in this scenario. The paper demonstrates the effectiveness of the proposed approach in solving the obstacle problem, highlighting the importance of understanding the evolution of losses and convergence behavior for optimal neural network performance. The paper presents a visual comparison of the exact solution and the neural network's approximation for a 1D obstacle-constrained ice sheet model with p equals 4. The loss behavior during training is also shown, highlighting the evolution of different losses such as the total loss, loss influenced by coefficient alpha, and loss affected by coefficient beta. The L1 error between the approximated solution and the exact solution is computed, demonstrating the convergence and prediction accuracy of the neural network. The approach is then applied to solve the obstacle-constrained ice sheet partial differential equation, PDE, in a simplified 2D domain, followed by its application to a realistic obstacle geometry using the Greenland bedrock elevation data from the National Snow and Ice Data Center, NSIDC. This dataset offers comprehensive information on various parameters related to Greenland's ice melt and movement, including detailed insights into Greenland's topography, digital elevation models, ice thickness, and bedrock elevation data. The parameter range is extensive, with DEM values ranging from 0.1 meters to 3,278.3 meters, ice thickness measurements extending from 0 meters to 3,366.5 meters, and bedrock elevation data varying between 963.1 meters and 3,239.0 meters. These data are used to evaluate the adaptability and robustness of the proposed algorithms. The dataset NSIDC 0092, comprising 301 columns by 561 rows, provides a comprehensive and granular view of the ice sheet in bedrock topography across Greenland with a spatial resolution of 5 kilometers. This grid resolution ensures precise climatological and glaciological analyses. The bedrock topography from the dataset is visualized in Figure 12, serving as our obstacle function for the subsequent analysis. When employing conventional random initialization, the neural network behaves erratically due to its failure to satisfy the obstacle, leading to numerical issues. To overcome this, a two-stage modeling approach is taken. In the first stage, the neural network is intelligently initialized by training it to mimic the bedrock elevation as illustrated in Figure 12. This preliminary training phase enables the neural network to learn and approximate the patterns of the bedrock topography. This is not a solution to the problem, only a method of initializing the network. In the second stage, the initialized network is trained to approximate the PDE, the same method as previously. This approach addresses the challenge introduced by the bedrock obstacle data from Greenland's ice thickness data and ensures that the neural network behaves predictably and accurately. The authors employ a neural network to approximate the solution to a partial differential equation, PDE, governing bedrock elevation and ice thickness in Greenland. Pre-training the network on the bedrock elevation data produces an initialization that facilitates a more efficient learning process, resulting in considerable error reduction. The penalty parameters alpha and beta are set to 4000, ensuring all weighted components of the loss are of the same order of magnitude. The adopted architecture consists of 15 hidden layers, each with 320 neurons, and undergoes training for 22,000 iterations to ensure accurate convergence and approximation of the Greenland ice thickness data. The training process yields an approximated solution, which is compared to the exact ice thickness data derived from the NSIDC 0092 dataset. Figure 14 illustrates this comparison, showcasing the neural network-derived approximation for p equals 4 alongside the precise data. To assess the performance of the approximated solution, the authors analyze the training losses, acknowledging the challenges in evaluating the solution's accuracy due to the lack of an exact solution and the non-interpretable nature of training losses in absolute terms. Instead, the authors compare the properties of the neural network solution to the ice sheet thickness data, recognizing that the thickness data itself may not necessarily be a solution to the PDE. This approach enables an indirect evaluation of the approximated solution, providing insights into its performance. The pre-training stage and the subsequent training process, along with the chosen architecture and penalty parameters, contribute to the neural network's ability to approximate the solution to the PDE, offering a promising approach for tackling complex problems in glacier dynamics. The paper presents a novel approach to solving intricate problems related to the dynamics of Greenland's ice sheet by integrating mathematical modeling and deep learning. A robust theoretical framework is established, illustrating the underpinnings of variational inequalities and obstacle problems. The authors leverage the power of neural networks to seek solutions, demonstrating both theoretical and practical applications. A key highlight of their methodology is the integration of pre-training. By first acquainting the neural network with a representation of the bedrock topography, they ensure a more efficient learning process when the actual ice thickness data is introduced. This strategic move not only optimizes their results but also underscores the importance of judicious model initialization. The authors compute the losses that would be found from inserting the measured ice sheet data into the three loss terms, providing a benchmark for comparison. They then show the trajectory of the losses as a function of training iteration, with results indicating that all losses converge to an absolute level consistent with the real ice sheet thickness data's satisfaction of the PDE. This suggests that this approach well approximates the solution to this PDE. Similar analysis was carried out for different p-values, with similar results. The paper concludes by summarizing the exploration of the integration between mathematical modeling and deep learning to address intricate problems related to the dynamics of Greenland's ice sheet, demonstrating both its theoretical and practical applications. This study demonstrates the potential of combining deep learning with mathematical models to investigate Greenland's ice sheet dynamics, showcasing remarkable accuracy when applied to the NSIDC 0092 dataset. The approximated solutions closely mirrored the exact data, highlighting the promise and potential of this interdisciplinary approach for climate science. The melting of Greenland's ice sheet plays a pivotal role in global climate dynamics, making precise and efficient computational methods paramount. The methodologies explored in this study can be adapted and extended to other similar domains, rendering it a versatile tool for the scientific community. By integrating deep learning with mathematical models, this research offers a promising approach for future research and problem-solving. As data collection and complex challenges increase, combining both tools will facilitate better solutions. The study draws on various mathematical and computational techniques, including the Galerkin least squares finite element method, the obstacle problem, and the deep Ritz method. References to existing literature, such as the work of Buehler, Piersanti, and others, provide a solid foundation for the research. The paper also acknowledges the importance of previous studies on ice sheet dynamics, including the work of Calvo et al. on doubly nonlinear parabolic obstacle problems and Juve and Buehler's research on steady, shallow ice sheets as obstacle problems. The author's approach builds upon these advancements, incorporating deep learning to enhance the accuracy and efficiency of computational methods. Furthermore, the study recognizes the significance of experimental observations, such as those by Kolstedt and Goldsby on superplastic deformation of ice. The author's methodology is grounded in a deep understanding of the underlying mathematical and physical principles, ensuring a robust and reliable approach. The paper concludes by highlighting the broader implications of this research for climate science and the potential for future applications in other domains. This research paper cites various works related to variational inequalities, elliptic partial differential equations, and obstacle problems. The authors draw upon a range of sources, including Kinderlehrer and Stampechia's Introduction to Variational Inequalities, Kornhuber's monotone multigrid methods, and Mayava and Tai's level set method for solving free boundary problems. The paper also references deep learning frameworks, such as PyTorch, and physics-informed neural networks, PINNs, for solving forward and inverse problems involving nonlinear partial differential equations. Additionally, it cites works on dynamical methods for solving obstacle problems in mathematical physics, and numerical solution of the obstacle problem by the penalty method. Furthermore, the paper incorporates finite difference schemes and partial differential equations, as well as deep learning surrogate models for high-dimensional uncertainty quantification. It also references convolutional neural networks with quantified uncertainty for heterogeneous elliptic partial differential equations on varied domains. The authors acknowledge the importance of Galerkin, least square finite element formulations for nearly incompressible elasticity, Stokes flow and iterative algorithms based on piecewise linear systems for solving bilateral obstacle problems. The paper demonstrates a comprehensive understanding of the existing literature in these areas, laying the groundwork for the development of novel methodologies and approaches. The cited works provide a foundation for the paper's exploration of the intersection of machine learning, partial differential equations, and obstacle problems, highlighting the potential for innovative solutions to complex problems.